Okay, so as everybody knows, our next speaker is Eduardo Dubuc. It's a pleasure to hear you to talk about transfer of Lax and pseudo functor structure.
So I start now?
Yes,
okay. Well, and this is the first time I am speaking in Zoom, so I don't know how it will come up. I am very happy to be back in CT meetings, and especially grateful to the organizer, which I imagine handle the software better than myself. Well, I start with the motivation for my transfer of structure of pseudo functors. Also, there has been a long time I don't speak English because of this COVID-19, so I have to recover my fluency in the language. We were working, trying to develop a theory of, this is motivation, okay? Trying to develop a theory of model bicategories inspired in the theory of model categories of Killen. And we use just the original Killen presentations of his theory, which we found a marvelous piece of mathematics. There is a beautiful symmetry, I recall you all, in this theory, and it's beautiful because both sides of the duality are necessary and are used. It's not that we have one theory and it's dual equivalent, no. Both sides of the symmetry participate in the development. Now, cofibrant replacement, you can see them there, illustrated in my slide. For each, that goes from model by category C into itself, but it's not a functor or a pseudo functor. It's just an assignation. From the actions, immediately follows, I mean, we have no work almost to do, that for the X, each object and each arrow of C, we have a cofibrant object, Qx, together with a trivial cofibration from Qx into X. And for each F, we have Q defined on F, okay? And we have this square diagram here, which looks very much, it is exactly what the diagram that appears in the notion of a pseudo-natural transformation. So if Q were a pseudo-functor, we would have a pseudo-natural transformation from the identity, from Q into the identity pseudo-functor. But here we have only the pieces of data with nothing else. Now, this is just interesting because we have to do no work for that. It just comes from the action. Now, where does it cofibrant replacement pseudo-functor? Well, it belongs at the level of the homotopic bicategory. This homotopic bicategory has the same objects than C, the same arrows, and the homotopies, Killen's homotopies, are not taken to generate an equivalent relation between arrows, but are left like themselves as the two cells of a bicategory. So in this bicategory, the two cells are the homotopies. And we have to put an equivalent relation between homotopies, if not, the things don't work. Well, there's many reasons why for this homotopy between homotopies, but it's not the subject of this talk. Now, once I have said this, we realize that the pseudo-functor structure for Q here was obtained by a transfer of the pseudo-functor structure of the identity along the theta theta f. So we transfer the pseudo-functor structure of the identity into Q. And this will give you the pseudo-functor Q. But this general, the correct generality is for lax functors. I mean, in my opinion, pseudo-functors always have to have the direction of the two cells, even if they are invertible, have to be put in evidence. So they are just like lax functors with an additional property. Now, the key fact that will allow to do this transfer was the thing which is inside this rectangle here. Look at it. We have the homotopy category, and if we compose with, if we compose afterwards with a trivial fibration, then this functor is full and faithful. This means that any two cells here comes from a unique two cells there. Each two cells here comes from a unique two cells there. This it reflects in the context of bicategories, lemma 5 of Quillen that says in model categories, these two are just sets, not categories. And lemma 7 of Quillen says that P lower star is a bijection between these two sets. Now we rescue this lemma and show that this is full and faithful. Even more is true. I mean, it's an equivalence of categories, okay? But for the transfer of structure, we don't need the full notion of equivalence, but just the fact that the post-composing is full and faithful. And also, for the dual theorem that we are going to see immediately, we shall need the other pre-composing with P also should be full and faithful. Now, we have been very careful, not very careful, but we were always trying, and we were successful to develop a perfect duality, meaning that everything is every concept here with us has a dual concept, and this is, I think, is one of the most beautiful characteristic of the model categories of Quillen, and he will rescue in all our developments this fact. Now, here I start the talk. I mean, I already 8 minutes. So we develop the general theory, which will be applied to what we were talking before. Pre-assignments and assignments is a notion that we introduce here, and they are like lax functors stripped of part of their data. So if we have bicategories, this is obvious. If we have bicategories, and F, a pre-assignment F from B to D is just defined on objects and arrows, and to each two objects and F, it defines Fx, Ff, Fy. Now, an assignment, it has already some more structure. An assignment is a pre-assignment, but it's also defined on two cells. And it's defined on two cells in a way that is functorial for the vertical composition of two cells. You will see that we are approaching the notion of lax functor, because a lax functor is all this plus monoidal multiplication, as shown here, with the corresponding identity arrows. So Lax functor is like a monoid, and is a pre-assignment, which is also an assignment and which has this monoid structure in addition, with the usual associativity and unit actions for a monoid. So you see, imagine, forget all this, imagine a monoid in a category of sets. If we have a set furnished with a bijection into the underlying set of a monoid, then this set can be furnished with a monoid structure in a way that this bijection becomes an isomorphism. This is a transfer of the monoid structure from the underlying set of a monoid into another set. And the bijection is, we thought of the bijection as transfer datum. So here we are going to be transferring all these structures of assignment and Lax functor to pre-assignments. Well, I mean, if I show you the next slide, you will understand better, I imagine. Okay, so we have pre-assignments. Remember, pre-assignments are only defined on objects and arrows. A transformation, this will be is the concept corresponding to pseudo-natural transformation, or Lax transformation. A transformation is as it illustrated here. You see, it's the same as when you start to write down what it would be a Lax transformation between Lax functors. So there are a family of arrows, fx, gx, and these two cells that establish the pseudo-natural notion. But here there is no actions. We have only transformations between pre-assignments. Now, if f and g happen to be assignments, you see, this goes from f to g. Now, if g is an assignment, then this data of a transformation is supposed to satisfy these actions. This action we see here is just one of the actions of pseudo-natural transformation. Now, if the assignments are Lax functors, also meaning that it has also the monoid structure, then we ask the transformation to satisfy the morphism of monoid actions. And we arrive to the notion of Lax natural transformation between Lax functors. So then we define modifications in the usual way. It's a family of two cells between this theta x and eta x. And the usual, this is the usual notion of modification, of action of modification. So modifications are the same for transformations, assignment transformations, and pseudo-natural or Lax transformations. Now, we have introduced another, well, this, what we just have done, define, you see here, we define 4 categories, functor categories, I would say. The category of pre-assignments, the category of assignments, and the 2 categories of Lax and the category of pseudo functors. And have forgetful functors because an assignment is a pre-assignment with an additional structure, and the Lax or pseudo functors are assignment with an additional structure. And we have these forgetful functors. And we are going to lift or somehow structures going up in the diagram. Now, I come back because we have introduced, for the purpose of this work, a notion of quasi equivalence. Quasi equivalence maybe are defined somewhere in the literature, but we have no reference for them, is in a bicategory X, any bicategory X, a quasi-equivalence is just an arrow such that post-composing and pre-composing with it is full and faithful. Obviously, this is a characteristic that have the equivalences. Quasi-equivalence is a weaker notion. And we have a proposition, a result that says that if we have a transformation in any of the categories, which is a quasi-equivalence in D for each X, okay, we have here in the functor category, in any other one, we have a transformation. Remember that the transformations are the arrows in these categories, which if we evaluate at X in B, we get an arrow in D, and this arrow is a quasi-equivalence. Then it is a quasi-equivalence in these functor categories, okay? So this we call pointwise quasi-equivalences. Now, the result is that pointwise quasi-equivalences are equivalences, but the other way, it doesn't seem to be true. It's a little bit, reminds me a little bit of the notion of, on the functor categories of pointwise limits, pointwise scan extensions. Well, here we have pointwise quasi-equivalences. It's stronger than quasi-equivalence. Equivalences are a particular case of quasi-equivalences, and there is an equivalence. It's well known in the literature, pointwise equivalents are the same as equivalence. Now, a transfer datum is a morphism in one of these four categories, such that theta f is invertible and post-composing with theta x is full and faithful for W in the image of F. So it's a more weaker concept that will be a quasi-equivalence. And it's necessary for the applications, and it's only used in the proof that W has to be in the image of F. This is a kind of morphism in these three categories. Now, our theorem is the following. If we have a transfer datum from F to G, then if G is an assignment, has an assignment structure, or if G has a lax functor structure or pseudo functor structure, then F can be uniquely furnished with the respective structure in such a way that theta becomes a good morphism, a good transformation, okay? So we can transfer, under this hypothesis of transfer datum, the structures of G into F. This is why this we call backward transfer. Remember, in the coequivalent replacement, we are transferring back the pseudo functor structure of the identity functor into the coequivalent replacement. Now, we have a dual definition of up transfer datum and a dual theorem of forward transfer, in which we transfer the structures from F to G, okay? So we have these two theorems, or one theorem as is dual, which have the are equivalent. Now, to have an idea of the proof is just impossible to explain all these equations, but you will see, suppose we want to transfer the definition of G in a two-cell for F. Then we consider this mu, which is a two-cell here in this D, and here you see I signaled the definition of G in alpha. Now, so this two-cell comes from a unique two-cell in here. And so we manufacture it to cell mu here, that it comes by the hypothesis for a unique to cell there. We manufacture this to cell with the definition of G in alpha. And with this way, we define F in alpha. F in alpha is this beta such that composing with beta gives you this mu. So we have used G in alpha to define F in alpha. Everything is beautiful. It has to be work because the category formalism correct that we had found leads you to the general correct generality, and then the proof follows. You need some work, of course, but all the work has been done in order to find the right formulation of the statements. Something similar happens for the multiplication. We use the multiplication of G in order to define the multiplications of F. Now, finally, you see, if we have any two categories and kind of forgetful functors, LAC define equifibrations. If you have a fibration, if you have an equivalence in Z, and we have an arrow here from X into the underline of an object up, then there exists a unique X prime, E prime that goes into here. So we find this is notion of LAC of equifibrations can be also considered for another type of arrows in Z, which are not necessarily equivalences. And so we have transfer datums and quasi-equivalences in Z, and our theorems show that there are fibrations in this sense of LAC. I mean, if an instructor in X can be transferred, an instructor in Y can be transferred in instructor in X. So our theorems of transfers of structure for pseudo-functors are examples, establish that certain arrows are fibrations in this sense. And with this I finish my talk. So I'm welcome to any kind of questions that somebody may have. Okay. It's all right. I mean, I don't hear anything.
Are there any questions or comments? What about online? Yes. Can you put him on? Steve?
Well, if there is no question, I would like to make a question, make a comment.
Yes, let's first listen.
A comment.
Steve Audi has a question. We are just trying to connect him.
Well,
sorry. No,
and
sorry,
then
I
we'll make
didn't.
your comment at the end, okay?
Yeah, sorry, I didn't have a question.
Okay. Well,
Okay.
I would like to make this comment for people
Please,
interested, for people interested in model categories. You see the cofibrillant replacement. Sometimes they put a pseudo functorial a functorial way of doing the factorization, a functorial factorization for model categories that will give you a cofibrillant replacement at this level. But for me, the cofibrillant replacement belongs in this level and is always there, even without the action of functorial factorization. And it has many advantages because in my opinion, the functorial factorization has many drawbacks, but this is not the moment to discuss. I just wanted to say that. Well, if there is no more questions, we can
No more questions. We thank you again. Thank you. Really.